Hello everyone and welcome back to Pharma E-Class. I am Anindya Goswami, and in the previous lecture we have discussed about the mechanisms of heat transfer as a part of the heat transfer chapter. So today we will discuss about convection, which is another important mechanism of heat transfer. Now convection process can be defined the process in which the heat flow is achieved by the actual mixing of the warmer portion with the cooler portions of the same material. And basically the convection can be classified into two basic types, that is the forced convection as well as natural convection. Let us see what are those things. Forced convection can be defined as the heat transfer convection process in which the mixing of fluid may be obtained by the use of maybe a stirrer, maybe a pump, maybe an agitator for the recirculation or for the fluid flow. For example, in forced circulation evaporators, the evaporating liquid is forced through tube under pressure. So that is there the forced circulation or forced convection is observed. Come to the natural convection. It is defined as the heat transfer convection process in which the mixing of the fluid occurs by current setup when body of fluids is heated. So there is no agitator or there is no forcefully transfer of the fluid, but the heat is the convection occurs naturally after the body is heated up or the fluid is heated up. For example, in pan evaporator, the convection currents are set up in the evaporating liquid. In general, fluid flow may be described as either laminar or turbulent, as you have already known from the previous lectures of the flow of fluids chapter, and this creates the problems in estimation. Now when heat is passed through the tube, the stagnant films determine the rate of heat transfer, and when the fluid flow is viscous, velocity is zero at the actual surface of the wall, it means that the layer of the fluid adjacent to the wall acts as a stagnant film, and comparatively stagnant film can be observed even in some turbulent flow as well. Now sometimes some scale formation also occurs. These scales are deposited on the surface of the metal wall and heat must be conducted through the scales. Now when steam gives up the latent heat, the water will condense on the surface of the vessel or maybe on the tube, on the surface of the tube, and again the heat must be conducted through this water film, and for heat transfer in the tube, heat must pass through any stagnant film by conduction as well. Come to forced convection. To explain the forced convection, we have to look into the figure containing the temperature gradients in a forced convection. So this is a particular metallic wall, and let us see how the fluid is being flowing and the forced convection is occurring of heat. The forced convection is occurring. So forced convection is a heat transfer convection process in which the mixing of the fluids is actually obtained by the use of a stirrer or agitator or pumping the fluid for recirculation, as I have already discussed in the previous definition. So we consider a case of heat flowing from a hot fluid to a cold fluid through a metallic wall. So this is the metallic wall, and this side, this is the hot fluid and this is the cold fluid. So definitely the variation of temperature at different specific point will definitely be observed, and this is given in this diagram. If you check the diagram properly, so that this is the temperature is increasing like this side, and there are different points like T2, then TE, then TD, then TD1, that is TB, T1, TA. So at different variation, because the temperature is varying and this is the particular distance, and the heat is also flowing, so there are different points or the different gradients of temperature which is explained in the adjoining diagram. So this is another format of that same diagram. So these are the different points, this T2, TE. Let us come to one by one. Metal wall characteristics. The dotted line HH, yes, this is the dotted line H and H. What is the C and CC? Obviously, C and C. It represents the boundaries of the film in viscous flow of the hot and cold sides. The gradient through the line TC and TD caused by the flow of heat whose conductivity is known. Now the metal wall may be of thickness L. Now hot fluid side, come to the hot fluid side. This is the hot fluid or the turbulent side. We are coming to the hot fluid side. To the right of the HH, that is to the right of the HH, this is the HH is given as dotted line. So in the right of the HH, the fluid is in turbulent flow on the hot side. The TA is the maximum temperature in the hot fluid. TB is the temperature at the boundary on the hot fluid, on the hot side or the turbulent and viscous flow junction. TC, we are continue to the hot side only. TC is the temperature at the actual interface, that is the boundary interface, and the curve TA, TB, TC, they represent the temperature gradient from the bulk of the hot fluid to the metal wall. Now come to the cold side. To the left of the CC, this is the CC, the dotted line. To the left of the CC we have the fluid is in turbulent flow on the cold side. So TF is the minimum temperature of the cold fluid. TC is the temperature A at the temperature at the boundary of the cold side, and TB is the temperature at the actual interface, that is between the fluid and the solid. The curves obviously TD, TE and TF represent the temperature gradients from the metal wall to the bulk of the cold fluid. Now come to the surface or the film coefficient, because in force convection we have to quantify the value of the surface coefficients as well. So heat transfer is occurring definitely, and that's why we are studying. So the film coefficients is the quantity of heat flowing through unit area of the stagnant film per unit drop in temperature. Now it is the conductive capacity of the stagnant film or for the transfer of heat which is required. Now let Q watt, that is joules per second of heat, is flowing from hot fluid to the colder one. The same heat must pass through the stagnant fluid film on the hot side through the metal wall, this is the metal wall, and through that stagnant film on the colder or the cold side. Let the area on the metal wall on the hot side is A1 meter square. The area on the square meters. The area of the metal wall on the cold side be A square. That is A2 it is given, that is in meter square and square meter only. So the average area of the metal wall is AM in meter square. The surface or film coefficient on the hot side, that is on the hot side, the surface of the film coefficient can be defined as the amount of heat flowing divided by area into the difference in temperature, or if we represent it mathematically, then H1 is equal to Q by A1 T1 minus Tc. From these two equations, it can be seen that the surface coefficient H1 of this particular film can be demonstrated and can be determined using that particular transfer coefficient. So from the definite mathematical expression we can find that the film coefficient on the hot side is given by the amount of heat flowing divided by the area into the difference in temperature, or in other words Q divided by A1 into T1 minus Tc. So this term is important and we are only quantifying the hot side. Since L divided by K is the resistance for the metal wall, now 1 per H is known as the thermal resistance, that is to be considered also. So the thermal resistance is due to the combined effect of the viscous film HH and the turbulent core. So the surface or film coefficient on the colder side can be classified as, or can be determined as, the amount of heat flowing divided by the area into the temperature difference, or in other words H2 is equal to Q divided by A2 into Td minus T2. Obviously these are the different this Td and T2 are the temperature gradients on the colder side, on the colder fluid. And 1 by H2A2 is the thermal resistance which is to be considered on the colder side. Come to the overall heat transfer coefficient, which is to be considered from the forced circulation, forced convection heat transfer mechanism. So overall coefficient can be determined in the overall heat transfer. Three resistance terms we have involved in this particular series. That is 1 by H1 A1 is the resistance on the hot fluid side. This L by K into AM is the resistance on the metal wall. And this 1 by H2A2 is the resistance on the cold fluid side. So the overall heat transfer coefficient, if we equate properly, then we can get as Q is equal to delta T divided by 1 by H1A1 plus L by K into AM plus 1 by H2A2. If both numerator and denominator of the right side of this particular equation are multiplied by capital A1, then we can get Q is equal to A1 into delta T divided by 1 by H1 plus L into A1 divided by K into AM plus A1 divided by H2 into A2, and the overall heat transfer coefficient U1 Wn square into K can be defined as 1 divided by the denominator of the above equation. So overall heat transfer coefficient, and this particular heat transfer coefficient we can write as Q is equal to delta T divided by 1 by H1 A1 plus L into K into AM plus 1 by this particular thing. So overall heat transfer coefficients, this U1 denominator is particularly that it is divided by the denominator of this above equation. So if we can determine the value of Q, that is U1 A1 into delta T, so the rate of heat transfer is equal to overall heat transfer coefficient into the area of the heating surface into or multiplied by the temperature drop. So this is the ultimate equation from which we can determine the overall heat transfer coefficient. Now come to the natural convection, which is the another form of the convection flow of heat. So natural convection is defined as a heat transfer convection process in which a fluid is heated and the currents set up, then only causes the mix of the fluid. In this type of transport, in which the fluid motion is not generated by any external sources like maybe an agitator, maybe a pump. So in natural convection, the fluid surrounding the heat source receives heat, and by thermal expansion it becomes less dense and then only it rises up. So the surroundings, the cooler fluid is then moved to replace, because thermal expansion happened and by the natural convection process the fluid which is surrounded by the heat source, it has received heat, it has risen up. So the surrounding, the cooler fluid then moves up and to replace it. The cooler fluid is then heated and the process continues forming a convection current. Now the process, this particular process transfers heat energy from the bottom of the convection cell to the top, because constantly some places will be filled and the cooler fluid will come, again it will get heated up and it will rise up. So this is how a natural convection current will be formed. The driving force for natural convection is buoyancy, and as a result of the difference of the fluid density. And this process continues, thereby affecting the mixing of both hot and cold fluids without any forced circulation mechanism, that is without maybe any agitator or maybe any pumps. Come to its application. The natural convection is observed when the extracts are evaporated in open pumps and not in closed or forced circulated evaporators. Thank you very much.